Hello, everybody. Hope you're having a great day. In today's unit, we are going to be talking about human energy and metabolism. And again, this is important as we start to understand how we break down food within the body that will impact, what types of calories and what types of nutrients we need to consume based on what our goals are, based on our metabolism and the different activities that we do throughout any given day. So let's take a look. So when we think about the term energy, what does energy mean? So energy is our capacity for work, and it's a dynamic state related to change. So, energy cannot be created or destroyed. We can simply transfer energy to various different forms based on the chemical changes that we can cause within those particular items. Okay, so energy is very dynamic and it's related to change. So when we think about bioenergetics, it's the flow and exchange of energy within a living system. So essentially what we're looking at is how can I take calories, how can I take food, break it down and convert it into some sort of usable form that I can utilize within the body. So energy metabolism is how our body transforms, uses, and stores energy that we've consumed in the form of food and drink. And we can kind of manipulate that based on the needs of the body. That can vary from day to day or from person to person. So pretty freaking cool. The diversity of these channels or the diversity of the transformations that we can make based on the needs of the individual. So we have three different types of biological work. We have chemical work, we have transport work, and we have mechanical work. And I've got a slide for each to kind of explain what's going on with each of these. So let's start with chemical work. So chemical work is essentially our ability to break down molecules and transfer those through the modification of chemical bonds. So here you can see the three different types of foods or macronutrients that we can consume. We've got amino acids, we've got sugars, and we've got fats. So amino acids are kind of the most simplistic version of our proteins. We have glucose, which is our carbohydrates, and we have fatty acids, which we know as fats. And look at all these arrows. So each of these arrows shows a potential change in those nutrients based on the needs. Okay, so again, check out glucose. Glucose has a lot of different options in terms of manipulations. And again, that certainly tells us that glucose is really important in terms of keeping our metabolism rolling. And again, we'll talk in more detail about that, but check it out here. So you can store things in the form of triglycerides or in our adipose tissue. We can store sugars or glucose in the form of glycogen, and that can be within the liver. And we can also store sugar inside the muscle as well. Inside the muscle, we can also store these amino acids, and these amino acids or protein particles can be used to build up muscle amongst other structures as well. So that's kind of a brief summary of what's happening with chemical work. Biological work or transport work is the energy from ATP that's used to move a particle from like low concentration to high concentration. So again, it's the energy that we need to move things against their concentration gradients. So here you can see an example of active transport, and active transport involves the movement of these molecules against their gradient. So again, think of them as like swimming upstream, and to swim upstream, it's a lot of work. So we need to invest quite a bit of energy in order for that to happen. And we'll invest ATP, which is our energy currency, in order for us to complete transport work. Okay, and transport work is important in a lot of different areas within the body. So it's really important that we maintain or establish these different gradients in the body in order for us to maintain contractility or excitability within some of the different cells of the body. Then lastly, we have mechanical work. And again, a large amount of the calories that we expend, or a large amount of the energy that we expend, will come in the form of mechanical work. And mechanical work can mean contracting of muscles, which is kind of shown in our image here. So again, when we contract our muscles to move, that requires mechanical work. But mechanical work can also mean movement inside the body. So we have something called smooth muscle, and smooth muscle can be found like surrounding our digestive organs, and that's going to allow us to move food through the digestive tract. We also have cardiac muscle in the heart, and that's going to allow us to move blood within the cardiovascular system. So mechanical work can mean movement of muscles, but it can also mean movement inside the body as well. So what is metabolism? So metabolism is the sum of the energy required to power all these cellular processes. So again, think of taking all of the energy that we need for transport work, for mechanical work, and for the chemical work, and putting those together, and that tells us our total amount of energy that we need. So we're going to digest carbohydrates, fats, and proteins and convert them into ATP so that we can use this for all three types of work that we just discussed. Okay, so we've talked about how we want to spend our energy. Okay, so we talked about the three different ways in which we expend our energy, and this shows us the three energy systems. So this shows us the three mechanisms through which we can expend that energy. So we have the ATP PCR system, we have the anaerobic lactic acid system, and we have the aerobic system. Okay, so a little bit of detail here about each of these systems. So the ATP PCR system, or the ATP CP, which is creatine phosphate system, is short in duration, 1 to 12 seconds. I know this says 20 seconds. I think it's more like 12 seconds. It's anaerobic in nature, which means it does not require energy. It does not require oxygen, rather. And we're going to use ATP that's stored in the muscles, and phosphocreatine or creatine phosphate that's also stored in the muscle. So high intensity and short duration for the ATP CP system. Moving to that intermediate system, the lactic acid system, the system will last 1 to 2 minutes in duration. It's going to be a little lower intensity, but still a pretty darn high intensity. It's anaerobic in nature, which means that it's not going to use oxygen, and we're going to use sugars in order for us to produce energy in the system, and it will result in a waste product, or a byproduct, I should say, of lactate and hydrogen. Okay, and then lastly, the aerobic system is 2 minutes or longer. This is aerobic in nature, which means that it requires oxygen. And our fuel options here are fats, carbohydrates, and proteins. However, we don't necessarily want to use proteins, because proteins are going to be used for a variety of other tasks within the body that are not necessarily related to energy. So when we think about energy, we know that ATP is kind of like our dollar bill, right? So we know that we can use this ATP, we can get it in different ways, and we can use it for our energy needs that we've discussed. However, we also know that we have a limited currency. So we have just a little bit of cash. Think of it that way. Probably like many of us, like I maybe have $20 in my wallet of cash. However, I can use my debit card to go get more money, or use a credit card or whatever, right? So this is kind of that same concept. So we have just a little bit of ATP available. However, we're constantly doing things to produce ATP in order for us to do more work, right? So again, this whole system of metabolism is constantly working in order for us to get that ATP that we need in order for us to do the work that we need to do. Okay, so we know that ATP is the only source of energy used directly for muscle contraction. So again, think of this as kind of like the dollar bill, right? So this is a critical source of energy for muscle contraction, bodily functions. So we have to be using this, we have to be producing this kind of all the time in order for us to do the things that we need to do throughout our day. Okay, so ATP is made up of an adenosine backbone. And T means triphosphate. Okay, so we have the TP is triphosphate, and tri means 3, and it's made up of 3 phosphate bonds kind of hooked onto this adenosine molecule. Okay. In order for us to utilize this energy, we need to break down this molecule, this ATP molecule. And basically all we're going to do is we're going to snip off this bond. We're going to snip off one of the bonds of these phosphate molecules. And as a result, we're going to end with a DP, and D means diphosphate, di means 2. So we're going to have 2 phosphate bonds, the energy that is liberated through the breaking of this bond, and 1 inorganic phosphate kind of floating around. Okay, and that's kind of shown down here. So you have the ADP, which is adenosine diphosphate. So I have my adenosine molecule hooked to 2 phosphates. I have that bond, which allowed me to release that energy, and then 1 inorganic phosphate kind of hanging out as a result. Okay, so when we think about that first energy system, that ATP PCR system or the ATP creatine phosphate system, this kind of shows us what it looks like, okay? And this is our most simplistic system of our energy options. And basically what we're going to do is kind of that first step that I talked about. So the ATP is going to be broken down into ADP, a phosphate, and the breaking of that bond is what allows us to liberate energy. Okay, and then what we're going to do next is we're going to take that ADP, okay, we're going to combine it with phosphocreatine. We're going to take that phosphate molecule from the creatine, we're going to put it with the ADP, and that's going to allow me to make ATP again. Okay, and again, remember, ATP is your dollar bill. So the more dollar bills I have, the more energy I can do. Okay, or the more energy I have, I should say, the more work I can do. And how long does the system last? The system can last about 3 to 10 seconds. The system is very fast in nature, so we can do this process pretty darn quick because there's only a couple things that have to happen in order for us to do this. And it will produce a high amount of power. However, it's going to be very easily fatigued, right? So again, I can do things with a high amount of force, high amount of power. However, I'll be fatigued very easily. We also know that this energy system will occur in the cell cytosol or the cell cytoplasm. Okay, so the second energy system is known as the lactic acid system or the anaerobic glycolytic system or anaerobic glycolysis. It's got a few different names for it. But essentially what we're going to do is we're going to break down carbohydrates, and this can be in the form of glycogen or glucose. Those are kind of our two options. Glucose is kind of like our floating sugars that we have in the blood, and the glycogen is going to be kind of like our storage form of sugars. And essentially what we're going to do is we're going to break down those sugar molecules. We're going to get some ATP, and we're also going to produce this waste product. I call it waste product loosely. It's really not a waste product. It's we can reuse it eventually. It's not super bad, but in the moment it can be kind of bad. And the reason is lactic acid or lactate is going to also be accompanied by this little H plus molecule or this hydrogen molecule. And the problem with that is it's very acidic in nature. It's very, it's a high acid item. And so as a result, the body doesn't like love that because it feels kind of like burny sensation. So again, if you've ever done a workout, maybe in the weight room, or maybe it was running or something along those lines where your muscles start burning, you know, most likely what's happening is you're having this buildup of this hydrogen molecule associated with this energy system. Okay, so the end product of this system, again, is lactic acid. We also get ATP, and we also get this hydrogen molecule. Okay, so this system can be used in events that require near maximal effort for 30 seconds to 120 seconds. So, you know, if you think about this like in terms of like track and field, this could be like a 400-meter dash or an 800-meter run, kind of depending on your skill level. Those are going to highly rely on this particular energy system. And again, those are examples of like races or events where you feel that burning sensation when you're getting to the end of the race because you're really tapping into this energy system. Okay. So pros and cons of this system. Again, it's relative. It's like if you remember like the Three Little Bears, this is like that middle where everything's just right, type of thing. It's not too, the bed's not too big, the bed's not too small, it's just right. So when Goldilocks comes in, this system is like, it's pretty good at developing power, but it's also pretty good at like preventing fatigue. So it's kind of like that middle ground. It's that intermediate system, where it's got like moderate power and moderate fatigue resistance. So we'll kind of use it for a lot of activities that are like 1 to 2 minute in duration. But also we can use this a lot in like if you do like what I call intermittent sports. So you play soccer, volleyball, basketball, those sports where it's like, okay, I gotta sprint because I got the ball and I have a fast break and I need to make a layup or whatever, but then I'm gonna kind of back off. So you're kind of jumping in between some of these energy systems. So that type of sport would use this system a lot as well. Okay, and the last of the energy systems, and probably the most complicated, is the oxidative or oxygen system. And essentially, with this system, we can use carbohydrates, we can also use fats and proteins as well in this system. And we're going to break those down with the use of oxygen in order for us to produce a large amount of ATP. Okay, so this system will produce ATP slower, but it can produce a large amount of ATP, right? So it's not super fast, it's not super powerful, it's just kind of chugging along. However, we can produce a large amount of ATP. It just kind of is a little bit slower in terms of its force production. Okay. So aerobic glycolysis can be used to describe the process that starts up here where I have carbohydrates that are going to be broken down into pyruvate. Aerobic lipolysis can be described when we use fats. Fats are going to be broken down into something called acetyl-CoA, and that'll kind of be fed into this system. That's aerobic in nature. And then we also have the breakdown of proteins as well, that can also be aerobic in nature. And again, we don't prefer to use proteins in this particular pathway because proteins can be used for a lot of other things in the body. We don't want to necessarily use a huge amount for energy, but maybe it accounts for somewhere between 10 to 20% of our energy needs. Okay, so how do we measure energy expenditure? There's two different options here. We can do something called direct calorimetry, and essentially how this works is you're imagine being in like a enclosed, I don't want to say box, but like an enclosed room. And essentially what we're trying to look at is heat production. And the reason for that is approximately 40% of the energy that we liberate during these metabolic processes is used as ATP, and then 60% of it is going to be released as heat, right? So therefore, one way to measure energy usage or production is through measuring body heat, right? And again, this makes sense when you think about exercise. If I'm in the gym and I'm comfortable in my sweatshirt, normally as I'm on the elliptical or whatever, I start sweating and I get hot, and now I just need to wear like my tank top, for example, right? The reason for that is I'm producing a large amount of heat while I'm doing that work, right? The more calories I burn, the more heat I produce, the hotter I feel, right? So essentially, with direct calorimetry, we're just measuring that heat. This is kind of what it looks like when we think about this for the measurement of human energy expenditure. So here you can see kind of an enclosed chamber. We got a girl in here running on a treadmill, and there's water and tubes surrounding this chamber. And essentially what we're going to do for direct calorimetry is we're going to look at how warm the water gets as it kind of moves through these tubes around the chamber. Okay, so we're going to measure that temperature change that has become hotter through this heating process. Okay, direct calorimetry, very expensive, very slow to measure. Also, we know that not all heat is liberated that we produce. So some of the heat is stored in our body, and this is why our body temperatures increase during exercise. So this was kind of like the first thing that we were able to do in terms of measuring calorie expenditure. However, we have a little bit of a better option that I'm going to talk about next. Okay, so we can use this process known as indirect calorimetry. And with this process, you can see this is a little bit blurry on my side, but you can see this guy has this mask hooked onto his face, and that mask is going to measure his oxygen consumption and his CO2 production in order for us to estimate his metabolic activity or how many calories he's burning. Okay, so this doesn't account for anaerobic activity. However, we do know that about 95% of the energy that we produce is going to be aerobic in nature. So this will give us a pretty darn good estimate of energy expenditure based on how much oxygen we're using and how much CO2 we're producing. Other ways we can kind of measure our energy expenditure or total calories. We can look at physical activity questionnaires where we're kind of asking, how much activity does a person do throughout the day. We also have heart rate monitors that can kind of monitor our activity level, and ergometers. And ergometers would be like something like a treadmill or an elliptical where I'm looking at heart rate and it's also measuring how much force I'm producing while I'm on that elliptical. And that can give me a pretty good estimate of how many calories I've burnt while I'm on that treadmill, particularly if you enter in all the information that it asks. Like it'll ask like probably age and body weight. If we put that information in with the heart rate data, it gets a pretty good estimate for us. Again, a lot of the smartwatches now can give us a lot of good information about calorie expenditure. And some of that is through heart rate. Some of them will have like temperature monitors like inside the watch, like on the back side of the watch. So it'll tell you kind of what your temperature is. Some of them even have like what's called a pulse oximeter, and that tells us like our oxygen levels within the body. So pretty cool, like the things that we can do with that. So for example, I have a Garmin watch on right now, and it tells me it's first thing in the morning right now. So I've burnt 432 calories since I've been awake, I guess. And if I go back and look at like my last workout, which was a 2.7 mile run, I can click on that. And let's see, it'll tell me during my 2.7 mile run, there we go, all stats. I burnt 261 calories and my average heart rate was 126. So kind of cool, like what we can do and how that, how all this can kind of be tracked and kept track of with smart technology now. Okay. So again, we've talked about the places that we're going to spend our dollar bills. We've talked about how to get the dollar bills, right? And this kind of gives us an overview of what those tasks kind of look like, right? So we think about energy expenditure, we really have three different things, right? So we have resting metabolism, we have the thermic effect of food, and we have thermic effect of activity. Okay, so let's take a look at what each of these entails. So resting metabolic rate accounts for 60 to 75% of our total energy expenditure. And this can also be called like basal metabolism. So if you've heard of that before, it's the same thing. And basal metabolism is based on lean body mass, the resting upkeep of muscle, liver, brain, and kidneys. Okay, so again, this is just like the calories we need to kind of maintain those particular structures, right? So, think of it this way, like if I live in my house, even if I don't do anything in my house, like I still need to there's still going to be dust that accumulates. So I still have to upkeep my house, right? I still have to vacuum the floors and clean the windows and that type of stuff, right? So that's kind of what the resting metabolism is. It's just kind of maintenance of those items that you have. And it turns out the more lean body mass you have, the higher this resting metabolism. And again, think about that like in terms of house size. So the bigger my house is, the more things I have to upkeep, right? The more windows I have to clean, the more carpets I have to vacuum, stuff like that. So again, that's kind of a little bit about that resting metabolism. Thermic effect of food is accounting for about 10% of our total daily energy expenditure. And these are the calories that we need in order to break down the foods that we consume. Okay, so again, if I'm going to eat, like for breakfast this morning, I'm drinking my coffee, I'm going to have a bagel with peanut butter next. There's going to be an energy investment that I need to take that bagel with peanut butter, to chew it, to swallow it, to break it down in my stomach, to absorb those nutrients and be able to put them into whatever form I need them in for my bike ride that I'm going to do later, right? So again, it's just kind of like an energy investment that we need in order for us to break down food. And then lastly, the thermic effect of activity. This is the greatest variance from person to person, but this is how much energy I'm going to expend above and beyond just resting in order to complete my given tasks. And this will account for 15 to 30% of energy expenditure. Okay. Now notice that thermic effect of activity can include physical activity. So that can be like, I'll tell you about my day. I'm going to go feed my chickens later, which live like kind of on the back of our property. So I've got to walk down there. I've got to carry like a big, kind of like a jug of water down to them and a big thing of food. Again, I wouldn't consider that exercise, but it is a little bit strenuous to get down there and take care of them, that type of stuff, right? Physical activity can be just like your daily tasks. Maybe you, work as a waitress or bartender or something like that. So you're walking around a lot. You're really moving around a lot. Maybe you're working construction this summer. You're really doing a lot of physical activity during your workday. However, that's not a workout, right? That's something kind of above and beyond a planned exercise routine, right? So physical activity doesn't necessarily mean exercise. Exercise always means physical activity. Okay, so I said I'm going to feed the chickens. So that's one thing that I'm going to do as part of my physical activity. I'm also going to go on a bike ride. Again, that's a planned exercise bout. So that's going to also fit into this category as well, right? So thermic effect of activity can include exercise and non-exercise types of movements. Okay, a little bit more about the thermic effect of food. So the increase in metabolism occurring during the digestive, absorptive, and metabolic processes of energy yielding nutrients. So this will be about 5 to 10% of the energy that we consume, and it's greatest for proteins, then carbs, then fats. Okay, so for example, I said that I was going to have a bagel with peanut butter here in just a little bit. Because that's a high protein item from the peanut butter, that might have a greater thermic effect. Like the peanut butter will have a greater thermic effect in comparison to the bagel, which is a pretty simple carbohydrate. Okay. Larger meals will have a larger thermic effect in comparison to smaller meals eaten over several hours. Again, just think about that like it's more tolling if I were to have like that bagel with peanut butter. I'm going to have my coffee and maybe I'm going to have a banana and a yogurt too, right? Like that's a fairly good sized breakfast. So that's going to have a larger thermic effect than if I have like the bagel with peanut butter. And then in 2 more hours, I have that banana. And then in 2 more hours, I have that yogurt, right? So again, that's going to be more challenging for you to break down in comparison to like, multiple small meals. This I thought was kind of interesting. So you think about this thermic effect of food. These are examples of what are known as negative calorie foods. And I pulled these from the scholarly source of Pinterest. But essentially what we're looking at here are foods that their calorie content is lower than their thermic effect. Okay, so for example, if an apple is about, let's call it 60 calories, right? The thermic effect of that apple is more like 65 calories, right? So it costs you more to break it down in comparison to the calorie gain that you get, right? Notice that these are all fruits and vegetables. In order for them to have a negative calorie count, they have to be raw and in their like original form. I'm trying to look here of an example. So, for example, like I don't know how many people are going to eat zucchini raw, right? So, when I have zucchini, I like to cook it like sauteed with olive oil, for example, and like a little bit of salt and pepper. So again, you lose that thermic effect if you cook that item. Watermelon, that'd be easy for us to eat raw. Apple, again, that'd be easy for us to eat raw. If I were to take that apple, cook it down, take the peel off, and turn it into applesauce, again, I lose that thermic effect. So again, we can kind of, through processing, remove some of those bonds, or I guess kind of break down some of those bonds that we would otherwise naturally do inside of us. So what's my takeaway from this? It's best to eat raw fruits and vegetables. However, like I'm probably not going to eat raw asparagus. I'm not going to eat raw zucchini. So cooking those just causes us to lose that negative calorie effect. However, they're still really good options for us in terms of overall nutrients. Okay, non-exercise activity thermogenesis. So we are going to be expending some level of calories through non-voluntary physical activities such as fidgeting, maintenance of muscle tone, maintenance of body posture. And we have this brown adipose tissue that's kind of this special storage form of fats that's going to produce large amounts of heat without producing useful energy. And we might use that like when we're in a cold environment or something along those lines as kind of like a emergency reservoir, essentially. Okay, so what are some factors that would affect our basal metabolic rate or our resting metabolism? Okay, so we said the most important factor was the amount of lean body mass. So the more muscle mass you have, the greater your resting metabolism. Other factors that are important, we know that gender, body temperature, so being in extreme environmental conditions, whether that's like super hot or super cold environments, those will increase metabolic rate. Thyroid hormone. So again, if someone has a condition that's hypothyroidism, their metabolism is low. If they're hyperthyroidism, then their metabolism is really high. Aspects of the nervous system. So again, if you can activate the sympathetic nervous system through caffeine or stress or exercise, those will all increase our metabolism. Pregnancy, tobacco use. What else do I have? Physical activity, age, body weight, body size, body composition. So all those factors will play an important role. And we also know there's a genetic component to understanding our resting metabolism as well. So genetics will play a role in how many calories we burn at rest as well. So how many calories are we burning, right? So metabolic rate during submaximal exercise is based on the intensity. Okay, so if I do like a low intensity exercise, I'm going to rely heavily on fats. If I do high intensity exercise, I'm going to rely on carbs for my fuel source. But however, the total amount of calories will also vary. So I've given the example of doing the elliptical a few times. If I get on the elliptical and I'm just doing nice and easy and I'm not really pushing it at all, maybe I'm going to burn about 300 calories per hour on the elliptical. If I'm really getting after it, I'm really pushing myself and I'm going high in terms of a harder intensity, I might burn 600, 700 calories per hour. Okay, so the amount of calories that I burn per hour is going to be linearly related to the intensity. Okay, so the harder the intensity, the more calories I'm going to burn. During maximal exercise, we're firing on all cylinders. So we're going to use all of the energy systems that we talked about, the aerobic system, anaerobic glycolysis or that lactic acid system, and the ATP PCR system as well. So again, we're going to kind of rely on all of those, and we're going to use carbs as our energy source. The reason that we're going to use carbs is kind of the fastest energy system for us to break down. So carbs makes the most sense for us in terms of, which energy system I should be using when I'm trying to get a lot of energy. Okay, so exercise and metabolic rate. So all physical activity will increase metabolic rate. And again, when we think about exercise, it's kind of that planned activity. And we can think of the exercise metabolic rate, but also the thermic effect of exercise. Okay, so exercise metabolic rate is like how many calories per hour am I burning while I do the elliptical. So again, we said I could be doing 300 calories an hour if it's like a low intensity. I could be doing 600 or 700 calories as I'm doing high intensity. And the thermic effect of exercise is like, what's the like recovery cost of that exercise? Okay, so again, if I'm doing 300 calories, it's just a light, nice, easy exercise. I don't need a whole lot for recovery, right? I can recover pretty easily from that because it wasn't that tolling on the body. However, if I do a really hard exercise bout and my muscles are going to be sore, that thermic effect is going to be significantly higher, right? I'm going to, need more calories after the fact in order for me to recover from that hard exercise. Okay, so what's the most important factor in determining metabolic rate during exercise? It's the intensity, right? So how high is the intensity will be the primary determinant of how many calories I'm burning during that exercise. This just kind of shows you an example here of exercise intensity and metabolic rate. So our resting metabolic rate about 1 calorie per minute, sitting, writing about 2, and then running 20 miles per hour, 38.7 calories per minute. So again, a huge range here in terms of how many calories we burn based on what it is we're trying to do. How can I tell what my metabolic rate is during exercise? We can look at oxygen consumption. This is super precise. That's the thing where you have the face mask hooked up and we're looking at how much oxygen we're using in comparison to CO2 production. However, it's not super practical. Like you're not going to be in a lab to do these tests. You will if you're a kinesiology major, but otherwise you're not like going to be in a lab doing these types of tests. So other things we can use, we can look at heart rate. That's a pretty easy one. Like I said, when I mentioned the elliptical, a lot of those ergometers will have like a heart rate sensor where you can put your hands on there and figure out your heart rate, and then it'll tell you your calorie expenditure based on that. And those are pretty darn good estimates for us. Also, your smart watches, your Apple Watch, those types of things. If they have heart rate on them and you can select elliptical on there, those are pretty accurate as well in terms of kind of estimating total calorie expenditure. What are the best types of activities to increase energy expenditure? Really, any type of exercise or movements that are going to involve large muscle groups, running, swimming, cycling, walking, group exercise. I've mentioned elliptical, that's another good one. Home exercise equipment, resistance training, something where you're doing vigorous movements in your occupation. So I mentioned, bartending or waitressing, where maybe I'm going to have to walk briskly for my entire shift if it's busy, or construction or some type of manual labor that way, landscaping, and then various sports activities. Essentially, if you're looking to expend a large amount of calories, my best advice for you is to find something that you like, find something that you enjoy, and that, my friend, is your best option for activity to increase energy expenditure. Okay, so what energy systems am I using during exercise? Again, as we mentioned, the most important factor is the intensity, and most tasks are going to require a blend of each of these systems. So again, when we do sports, we're very highly likely going to be using all three of the systems. However, based on the intensity of the movement, will determine which of the energy systems I'm using. So a low to moderate intensity, we'll use the oxidative system. If you're doing something with pretty high intensity for like 1 to 2 minute bouts. So again, these can be like intervals, right? So let's say I go out to the track and I'm going to do 400-meter repeats, for example. I'm really going to be highly reliant on that lactic acid system, even if I'm doing like 6 reps, right? So it's going to be 12 minutes in duration, but each rep is about 2 minutes, okay? So that would allow me to highly rely on that lactic acid system. And then if I'm doing shorter bouts, so strength training, okay, so if I'm going to do bench press and squats, for example, I'm going to do 4 sets of 10, okay, to do about 10 squats is going to take me about 12 seconds, 15 seconds, something like that. So that's going to be highly reliant on that ATP PCR system, or that first energy system that we talked about. This kind of shows you the energy systems needed, during exercise, kind of separating out anaerobic versus aerobic. Okay, so our anaerobic systems are the ATP PCR system and the lactic acid system, and the aerobic system is that oxidative pathway. So here you can see the total amount of time. So here I have duration in seconds versus minutes. So if the duration is 10 seconds in duration, about 90% of the energy is coming from anaerobic and about 10% coming from aerobic. Okay, if I'm going to go 90 seconds, you're about 50-50. Okay, so I'm about 50% anaerobic and 50% aerobic. As I increase to minutes in my duration, okay, by the time I'm at 10%, or I'm sorry, at 10 minutes, I'm about 20 to 30% anaerobic and 70 to 80% aerobic in nature. Okay, so again, this just kind of shows you how we shift our energy system needs based on the duration of the exercise. Kind of cool. Okay. What about carbs versus fats? So fats are going to be our major energy source during low intensity exercise, but higher intensity exercise is going to rely heavily on carbohydrates as our fuel option. But we also have this crossover effect, and this shows us the point at which we're going to switch from fats to carbs or vice versa. Okay, so carbs become our major energy source when we're doing higher intensity exercise in comparison to fats. And again, training will increase our ability to use both fats and carbohydrates, kind of based on what type of training that we do. This crossover effect, again, just accounts for that interaction between fat versus carb choice in the world of energy expenditure. So here you can see the intensity associated with this crossover. Okay, so here you can see carbs and fats. Okay, so again, when we're at a low intensity versus a high intensity. Okay, at low intensity, I'm using about 80% fats and 20% carbs. As I increase that intensity to about 50% of my VO2 max, I'm using 50-50. So 50% fats, 50% carbs. And as I increase the intensity to 100%, I'm using 100% carbs and 0% fats. Okay. So again, I think, a lot of people think about this in terms of, okay, well, I want to burn fat. So I want to be in this fat burning zone in order to use fats as my fuel and lose weight that way. Okay. So what is this fat burning zone? It's the exercise intensity needed, like a low intensity, about 50% or lower, where fats theoretically are the predominant fuel source. So what's the problem with this? Okay, so although it's correct that the percentage of energy from fat increases when the intensity is low, we must be cautious in interpreting this as it relates to exercise. Okay, so if the goal of an athlete is to use as much fat as they can and spare sugars, then it's important to determine this zone. However, if our goal is weight loss, we want to think more about like total calorie expenditure, right? So again, when I'm at a low intensity on the elliptical, I'm going to burn fats, but I'm only going to burn 300 calories. However, if I do a high intensity on the elliptical, I can burn 700 calories, but it's going to be carbohydrates in nature, right? So again, when we think about losing weight or, creating this calorie deficit, our body doesn't care whether you're burning fats or carbs. We're interested in creating a deficit. And some of that deficit, most of that deficit, will end up coming from our fat storage. So what we're doing during the exercise doesn't necessarily matter in terms of which fuel we're using. It's more about just creating a deficit, right? So in my opinion, and in the opinion of a lot of scientists, it's important that we just create that deficit. So doing the higher intensity is going to be a better option because I'm burning more calories in that particular scenario. Okay, so this just shows you that example. So energy expenditure from carbohydrate and fat in low versus high intensity. So this shows us the percentage of calories. So walking at 2 miles per hour, I'm burning a lot of fats. In comparison to running, I'm going to use just a little bit of fats, mostly carbs. However, down here, this shows us the total calorie expenditure. So walking slow will burn 100 calories per hour. Running fast will burn 500 calories per hour, right? So again, if I can burn more calories by doing the higher intensity, that's a better option for us in terms of a weight loss. In addition to burning more calories during the exercise, we also get this thermic effect of exercise, also known as EPOC, or excess post-exercise oxygen consumption. And essentially, when I start exercising, I create this O2 deficit. And this is the amount of oxygen that I needed, but I didn't have yet. So if you've ever started running, for example, running's a great example, and it feels really freaking hard when you get started. Like, oh my gosh, am I going to be able to do this today? And after a couple minutes, then you're like, okay, like I got this, it's fine, right? The reason for that is it takes your body a little bit of time to adjust, right? So when you start the exercise, your body is like, oh, what? We're doing this? And it takes some time for us to adjust to the physiological needs. Then once you get warmed up, you're going to reach this steady state where things feel good, right? I'm able to get in enough oxygen based on my needs in order to kind of meet those needs. So life is good in this steady state. Okay. Then at the end of exercise, notice that your heart rate stays up and you're maybe still breathing heavy even when you stop the exercise. And that is our oxygen debt. And we need to pay that debt back once we're done with the exercise. And essentially, that debt is the amount of oxygen that I need or the amount of calories that I need to return my body back to its like original resting state. And again, the harder the exercise, the more debt I've created. And so therefore, the higher the calorie expenditure after the exercise is over. So the higher the intensity of the exercise or the duration of the exercise, the more damage has been done in the body. And I don't mean damage in a bad way. I mean damage as in like where we've depleted our fuels, we've like really worked our muscles. And so we have muscle fatigue, those types of things. So this is a good thing. The higher the EPOC is, right? So the more kind of these bonus calories I need after the exercise in order to get me back to that kind of that resting position. So just very quickly, we think about fatigue. So acute fatigue can be defined as our inability to continue exercise at a desired level. And this fatigue can certainly be related to nutrition and certainly be related to these energy systems. But it can also, I want to make sure that we appreciate that it can also be a lot of other things. Okay, so it can be peripheral, which is out of the muscles, like the neuromuscular junction and muscle cells, but it can also be central, and that can involve the brain and spinal cord and kind of some neural fatigue as well. So when we think about fatigue, again, just I want us to kind of keep in mind that it can be a lot of different things, right? There's a lot of reasons why we get to that end of that exercise and we feel just absolutely drained. Some may be nutrition, some may be some of these other aspects as well. So what causes acute fatigue in athletes? We have peripheral versus central fatigue. Acute fatigue during exercise is associated with an interaction between some of these factors. So some factors that may influence the brain and our ability for our muscles to contract. It could be an accumulation of some of the waste products associated with our energy systems. It could be depletion of our energy substrates, so our fuels. So maybe we run out of carbohydrates or we run out of ATP, and so therefore we're feeling, fatigue. And it could also be related to something neurally, as we mentioned, a reduction in motor unit firing frequency, and a result in a decrease in neural drive from the brain. So again, what do I want you to get out of this slide? Appreciate that fatigue is much more complicated than just I didn't have enough sugars, and so therefore, I had to slow down in this race or whatever it is, right? So again, just appreciate that fatigue is multifaceted, right? So there are many different things, many different reasons that people feel fatigue. Nutrition is just one of the elements that we'll kind of explore in this class. However, I just want you to kind of appreciate the broader picture here when we think about what does fatigue mean. And then lastly, when we think about delay of onset of fatigue or DOMS, right? So proper sport training is the most effective means to delay the onset of fatigue. Okay, so physiological training. So the more we train in our sport, and training those specific energy systems that you're going to need, the better we become, right? The more efficient we are at utilizing those. Okay, but then also think about, the psychological aspect of training as well, and how does that play in, right? How does my confidence, how does my mood impact my fatigue levels? Okay, and then biomechanical aspects. So how can I move more efficiently in order for me to potentially, delay my fatigue, right? So how can I move more efficiently when I do XYZ exercise in order for me to kind of prevent that fatigue? And again, we know that nutrition will play an important role in delaying fatigue.
and also kind of in that recovery process after the fact, following a high intensity exercise bout. So again, just kind of wanted to tie that together a little bit in terms of allowing us to see the broader picture when we think about our bodies and our health and how we can kind of become the best versions of ourselves, and how does nutrition play into that? But also, these other areas, these other aspects are also important in that grand scheme as well. All right, that is all for today in our unit on metabolism and energy. I hope you have a great day, and we will see you next time.